In this example, we want to graph two exponential expressions and two logarithmic expressions on the same set of axes. So we have y equals 2 to the x and y equals 10 to the x. When you go to graph an exponential like this, let's do y equals 2 to the x. It always has an anchor point, right, at 0, 1. Right? All exponentials share the same anchor point as long as they're not shifted around. And then the way you do this is you get a second point, you go over to 1, you just plug in 1 right here. Y of 1 equals 2. So there we go. Maybe we could do one more point. If we plugged in 2 here, we'd get 4. So 2 goes up to 4. So something like this. And this graph asymptotically approaches the x-axis, and then it comes along like so, hits that anchor point, and then starts to explode. There we go. Off it goes. Okay, 2 to the x. Okay, 10 to the x, so we'll do this was blue. 10 to the x, why don't we do this in red? The higher the base is, the steeper this thing blows up exponentially. So 10 to the x, when we put in 1, we get y equals 10 to the 1, which is 10. So it still goes to the same anchor point, right? They all go through that, and then we go over 1 up 10. So look how steep that is. Again, it approaches the x-axis asymptotically when you go out to the left, and then it comes in below 2 to the x, hits that anchor point, and then really just blasts off almost straight up. Not straight up, because then it wouldn't be a function, but almost straight up. Goes up even steeper here. Okay, so there's 10 to the x. Note if we put in 2, we'd be up to 100. So if we tried to go over 1 more on the x-axis and plot the next point, we'd be way, off the page here. Okay, so that's how exponentials work. The bigger the base, the steeper they go up, but they all go through this point here, 0, 1. 0, 1 is the anchor point for these. Now let's talk about logarithmics. Log base 2 of x, all logarithms, as long as they're not shifted around, they go through their own anchor point, which is 1, 0. Here we go, there's our anchor point. And a good way to think of how to get the second point here is that you look at the base, and what this means is it takes until 2 on the x-axis to get up to 1. I'll write that out. It takes until 2 on the x-axis to get up to 1. So something like this. And then you have to know the basic shape. So you need to have the basic shape of both of these, all 4 of these graphs. Really, you need to know what a basic logarithm looks like and what a basic exponential looks like is what I'm trying to say. So the logarithms approach the y-axis asymptotically, and then they kind of bend over and go off like so. Okay, maybe something like this. There we go. So there's log base 2 of x. And notice how 2 to the x and log base 2 of x are perfect reflections over this diagonal. If we drew in a diagonal line here, they'd be perfect reflections. So for log base 10 of x, which we will do in purple, it still goes to that same anchor point of 1, 0. That's our main anchor point for all logs that aren't shifted around. I'll write it in here, 1, 0. That's important. And it comes in here, it approaches the y-axis. It actually stays under 10 to the x, so that's not entirely awesome graph here, but then it hits that point, that anchor point 1, 0, and then here we have it takes until 10 on the x-axis to get up to 1. So it takes until 10, so we're all the way out here at 10 to get up to 1. So it's much more bent over. There we go. Something like that. Log base 10 of x. So with logs, the higher the base, the more sharply it bends over. Just like in the exponential case, the bigger the base, the more sharply it rises up. And again, you can see that 10 to the x and log base 10 of x are mirror images across that diagonal y equals x line. So this graph is already getting pretty busy, but we can imagine adding in also 5 to the x and log base 5 of x, 3 to the x and log base 3 of x, and making this nice array of all these different functions. I think with just these 4 graphs, you can get a pretty good idea of what happens with exponential graphs and logarithmic graphs.